So I will say welcome everyone to the 2020 Daniel and Irma Evans Endowed Lecture. And in particular, I'd like to welcome members of the Evans family. I think we've got a couple participating, as well as our speaker, UC Davis Distinguished Professor and UW alum, Jay Lund. The Evans Endowed Lectureship was established a number of years ago by Daniel, Roger, and Robert Evans to honor the broad societal outlook of their parents, Daniel and Irma Evans. This lectureship provides an opportunity for my wiener dog and for us to deepen our understanding of civil and environmental engineering by exposing us to new concepts, challenges, concerns, and methods that may affect our engineering research and practice in the years to come. Today, Professor Lund's lecture will provide the opportunity to deepen our understanding of the role that civil engineers as designers and builders of civil infrastructure play in ensuring the prosperity of our cities, but also the impact of our work has on public health, ecosystems, our health, and societal equity and justice. Professor Lund is the co-director of the Center for Watershed Sciences at UC Davis. He served on the California Water Plan Updates Advisory Committee as convener of the California Water and Environment Modeling Forum and as chair of California's Delta Independent Science Board. He's author and a major contributor to 2 Public Policy Institute of California reports addressing water management in California. One comparing futures for Sacramento San Joaquin Delta, and one managing California's water from conflict to reconciliation. Clearly an expert in water management. For his service and contributions to his field, he was elected to the National Academy of Engineering in 2018. Please join me in welcoming Jay Lund.
Well, thank you very much for that kind introduction, and it's a great honor to be a speaker coming back to my alma mater in many ways to give this talk. I somehow think that any moment now I could wake up in the computer room in Wilcox Hall still trying to figure out how to get some program to work for Steve Burgess's class or Rick Palmer's class or somebody else. But it's really quite an honor to be here. And I remember from that time being a student in Seattle, Governor Evans, and he, I think at the time, was president of Evergreen College, and all the great things that he did, and his constant dedication to bringing knowledge into government. And maybe I've had just some small opportunities along those lines in this career. So my talk today is a little bit different. This is not a research talk. This is more of a perspectives talk. So it's sort of an old man talk in a sense. I want to talk about the profession in general and some perspective thinking on the profession. Many people will have had many of these thoughts already, but hopefully this is at least entertaining and maybe thought-provoking in a useful way to all of you. I'll start off with this quote. Hopefully you can all see the slides from Sextus Julius Frontinus in 97 AD in his treatise on Rome's water supplies. Will anyone compare the idol pyramids or those other useless though much renowned works of the Greeks with these aqueducts, these many indispensable structures? And I think in civil engineering, this is what we specialize. We specialize in really impressive works that nobody talks about when they work. Sort of with the old saw that you don't know a civil engineer, you never know the name of a civil engineer unless their bridge fails. Okay, so there we go. So a slide of thanks to all the fine people at the University of Washington that gave me a great education, both in engineering and in people. Rick Palmer, who I guess is now department chair at UMass Amherst. Steve Burgess, who I'm pleased to see on this call, I'm honored. John Mayer, who was my advisor when I was a geography graduate student before I went across the quad to become an engineer. Colin Brown and Brian Marr, who were alas deceased, but were very important in informing my career. Colin Brown being a structural engineer, Brian Marr being an environmental engineer, and Rick Palmer and Steve Burgess, of course, being water engineers. And of course, my last thing here for the UW is the University of Washington Yacht Club, which is now called the Washington Yacht Club, I think now, which provided me much stress relief when I was a student at UW. Next raft of thanks I have to give is to the people of California who've paid for me all these years at the University of California, Davis, and have provided all kinds of wonderful water problems to study, both for me and my students. And of course, I have to thank all of my current and former students. This is a picture of a gathering at our home, and as I look at it, about 4 or 5 of these people are now professors in their own right, and scattered all over the world now, actually. It's really true that professors learn more from their students if they take a little bit of trouble than the students learn from the professors. I'm sort of living proof of that, and have benefited from that immensely. A little bit of outline. I want to start off at the beginning with sort of the main themes. Always put at the beginning of your talk what the main points are, so that if people fall asleep or get distracted, particularly on a Zoom call, they'll have at least seen the main event. I want to talk a little bit about the origins of modern engineering, and then talk about some modern examples with particular reference to some individuals that I think have embodied both the strengths and weaknesses of our profession in a few ways. And then I want to talk about some of the challenges to the profession in accomplishing the bigger missions of the profession now and into the future, into what will always be a changing times. I have some sort of maybe hubris thoughts on what it takes to be successful with problems, not from my own experience, but from having observed many others. And then some conclusions, and of course, because I'm a professor, I'll give you some further readings. But first, I want to present you all with a question. So here we have a very nice plot of deaths from natural disasters, annual death rates from natural disasters globally, from 1900s on to the present day. What I want you to notice is 1920s, 1930s, 1940s, 1950s, huge numbers of deaths from floods and from droughts. So in the water environmental province. We also had huge numbers of deaths that aren't on this plot from waterborne diseases during these periods. So I think the question is, how did we get from these huge rates of deaths to maybe on the order of 10% or less than 10% today from what they were then? We do have terrible problems today, but gosh, I prefer the terrible problems we have today to the terrible problems we had in the 1920s, 30s, 40s, and 50s. So we can take, I think, some pride and some perspective from the progress we've made, even as we should not be complacent about the problems we have today and for the future. So the main points I want to get across here is engineering is done for human objectives. I mean, we all kind of know this because people pay us, so people have to have reasons to pay us, and so basically we're all employed, and this profession exists because humans feel they have problems. Sometimes our human objectives for engineering are to manage ecosystems. So sometimes our human objectives get a little bit more altruistic, a little broader than just humans in a narrow sense. But nevertheless, some human had to decide that the environment was important before they're going to pay an engineer to work on it. And we as a profession sort of benefit from that. Essentially, almost all engineering, I would say really all major engineering, is done by organizing people. Nobody does these things alone. And so a substantial component of any engineering success is your ability, our ability, the profession's ability to work with others, both within the profession and outside, to get a problem solved, to muster the construction workers, the design workers, the planning workers, the data collectors, the taxpayers, the politicians, the lawyers, so that the society can actually accomplish some engineered objective. And we're just there to basically help make sure all those details are attended to and they make sense and they work better than they would otherwise. There's a wonderful saying from the 1800s about the definition of engineering is being able to do for $1 what any fool could do for $2. And that's to some degree a good social motivation for a lot of our engineering in the end. So a lot of engineering progress really relies both on social innovations to be paired with technological or technical innovation. So we'll see some examples of this later on in the talk, but pretty much every major improvement in technology, in order for it to be well used, has required major social changes. And many major social changes have allowed technological changes to also occur. So there's some kind of a interaction, interdependence on social progress and technological progress. They help each other as well as sometimes hurt each other, as we can all imagine from our acquaintance with history and politics and the like. And I think these first 3 points apply to all engineering at all times, at all places. The fourth point I want to make here really applies since the time of Galileo and the time of Louis XIV in France, as I'll talk about later, which is the success of the engineering discipline as we know it today really relies on the mathematical and quantitative languages that we've brought together to sort of add cohesion and integration and rigor, quite often, to the organization of truth. Think how hard it is to organize truth if you don't have math, if you don't have that common language, that common deductive logic that math gives us that symbolic ability to represent. But really, it's the ability of us humans to bring mathematics and quantitative language and reasoning to socially organize these truths, to organize not only the problems, but also the people to solve the problems. Sort of the next implication of that is technology is actually usually easier than people in terms of managing them and to actually provide an engineering solution. And I think all of our elections really demonstrate that quite nicely. And then the final point I want to make is engineers often get blamed for a lot of problems. And I think sometimes that's true. Sometimes every solution brings a new set of problems. In many cases, most cases, I think the new problems are better than the old problems. And so maybe that's a mark of progress. But engineering throughout time has both supported stability and change. The kind of prosperity that we see in our societies that come from a lot of engineering, certainly in civil engineering, provide a foundation for an ability of the society to change in very positive ways in many cases, and in some cases in bad ways. So I think engineering supports both stability and change for good and bad. And this is another common constant, I think, across really millennia of engineering projects. So for civil engineering, all civilizations have infrastructure, and this goes back to the ancient times. I'm going to turn my light on to maybe light my screen up a little better. So starting about 3,000 years ago or so, we had the first major civil works projects of Mesopotamian agriculture and the Indus Valley and a few other places that all have had engineering challenges in some ways. And they all had to organize people to do this, and they had to organize technology. And I don't think they had very much math for most of this, but they had some probably early conceptions of math. China also, this is not restricted to any part of the world. This is a common human propensity to engineer, if you will. The great Emperor Yu of China, 2000 BC, there's a picture of him. He what really made him emperor at the time was his ability to control floods. He organized people to not just build levees, but also to have controlled flooding of the floodplain and to dredge out channels to send the floodwaters down particular channels and not to burst levees. So we still do this with the Sacramento bypass for flood control in California, and the bypass systems in the Mississippi. Some of these ideas, the conceptual ideas of this engineering goes back, really 4,000 years in some ways. And then I will probably mispronouncing this, but I'm sure some of you will know how to actually pronounce it. The Dujiangyan irrigation system in China from 2000 BC. You can see at a very thoughtful way of diverting stream flow from the river near Chengdu. You'll notice that the diversion is on the outside of a bend, so that it has less sediment coming through. And just to give you a sense that you don't see in the schematic from this picture, that this is a very sizable river. And this is a water diversion that irrigates several 100,000 hectares of agricultural land. Persia and Greece, they had their own engineering works from very early times, and this is an example of the qanats. It's one of my favorite words, qanat. It's a great word, no U in it. But it's a way of collecting groundwater. Some of you water folks might have seen it, but I had to have some groundwater in there because groundwater is very important these days as well. And then the tunnels that were built very early on. So here's a tunnel from across the island of Samos in Greece from 550 BC. And you can see in this lower diagram the path of that tunnel from both sides. And they almost made it match up. And at the end, you see they had to swirl around to find each other. And then, of course, Rome, the quote from the beginning on Rome's water supply system. Here you can see some fine pictures from about 1000 BC and 400 AD. And we see these aqueduct pictures and we associate them with Rome all the time, but most of their Roman aqueducts were actually canals and tunnels, or shallow tunnels, cut and cover kind of tunnels to keep the grade. And sometimes if they had a narrower passage, they would do this kind of a siphon where the pipeline was of lead. So lead was very expensive and hard to work. So when the construction of lead was be too much, they would build these larger aqueducts. They had quite a problem with lead poisoning, but not usually from the aqueducts, because the aqueducts were supplied by karstic aquifers, so they were not very acidic. And then, of course, in Central, South, and North America, we have all kinds of indigenous peoples that developed their own civilizations for periods of time that had tremendous irrigation systems, since we're mostly a water audience today. Really very interesting stories there as well, although we don't know quite as much of them because we don't have as much written material. So all of this pre-modern engineering, how was this infrastructure designed and built? Who organized it? Was it kings? In some places, they say there's some anthropological evidence and archaeological evidence that actually it was priests of temples that were in charge of organizing people to run these systems and manage them. Or was it village and sort of village elders and folks? Who financed this? Was it the king levying, saying you will all go build this stuff? Was it religious taxes or religious duties that were imposed on people to get them organized to build and maintain these very elaborate infrastructure systems at times? Who led these efforts? Was it a brilliant ruler? Was it some brilliant administrator or architect? Was it village leaders or experts, or maybe some combination of all of them? But clearly it had to be somebody that could figure out the local politics and economics and finance at the time. Even if they didn't have money, they had some kind of medium of exchange in terms of their labor, I suppose. But all of this pre-modern engineering had the same kinds of human problems that we have today. If you go back and read Fontinus's work from 97 AD, you'll think, oh my gosh, we have a lot of these same issues today as water managers, and we will 100 years from now, 1,000 years from now, we will have many of the similar people problems as we have today. How were these systems designed? You know, for us as engineers, how were these systems designed? Did they use mathematics? Clearly, the Greeks used quite a bit of mathematics. The Romans did, the Egyptians did, perhaps the Mesopotamians. And my impression is, and I'm not a specialist in this field, is that a lot of sort of surveying engineering, they did a lot of land surveying, who owned the cropland and who owns, you know, so that you would know who owned the crop that came off the cropland, was probably important for these kinds of open channel flow systems. And in fact, in the early American water systems, the Erie Canal was first built and engineered by basically land surveyors from New England and the Mid-Atlantic states. Those were the engineers of the time, because people paid a lot of attention and wanted to be very quantitative about who owned the land. And so the land surveying was one of the relatively exact sciences and expertise that was available to these civilizations, as well as in early in the United States before we had engineering colleges. And it's, of course, quite relevant when you're building open channel flow systems, because you want elevations and alignments to be quite right. So to what extent did they have experienced experts that were close to what you needed, like land surveyors, or to what degree was it folk wisdom or religious wisdom that had been somehow cultivated over hundreds of years? And maybe to some extent, I think to some extent what we see is the survivors of Darwinian selection. You know, we have these evolutionary algorithms that we use in optimization these days. Maybe we're witnessing the survivors of the surviving systems, and all the ones that didn't survive. Well, they're all gone and blown away, and we're just seeing the lucky ones that survived. There's probably a bit of that goes on. You see this with old buildings. You think, well, gosh, they built buildings really well back in the old times. Well, they probably all the terrible buildings fell down, and we don't see them anymore. It's probably true for canal systems and water systems as well. Modern engineering. I think modern engineering is very different. You know, we didn't have 12 years of education to get graduate degrees to do engineering back in Roman times. So in medieval times, Renaissance times, we started to see a fascination with mathematics and the attempts to apply mathematics to physics. You know, Galileo, I think, is pretty famous for this. And then we start to see, really, with the French, a lot of really formalization of engineering, particularly through the use of mathematics and empiricism, where you actually go out and see if something worked. And if it didn't work, why did it fail? And let's try to figure out why it failed so we make it work better the next time. Things that really are very common in modern engineering. And the origins of this, there's some really wonderful books on this, and I have some of them cited at the end of the talk, really came from the political ambitions of Louis XIV. Louis XIV in the 1600s, France, he was the king of France, but really all the power was in the nobles, in these feudal lords and all the different provinces. And so he was really dependent upon all of the feudal lords for their military capabilities and for their abilities to maintain the harbors and the ports and the roadways at the time. And so the king, you know, as all politicians do, he was looking for more power. And so he started off by centralizing the military, you know, so that he wouldn't have to rely on levying troops from the provincial lords. He would have control of the French army, which gave him tremendous economies of scale. And of course, if you're going to control the army, you want to control all the fortifications. And so if you're going to run a system of fortifications as opposed to a single castle, because each noble would maybe have one or two castles that they would control, and he, as the king of France, he would have dozens and dozens of castles. He wanted to have a group of experts that would work across all of these castles. And so famous engineer Vauban founded essentially military engineering as a discipline, kind of as we know it today, with some application of rational methods, some application of mathematics and scientific methods to both the construction and design of fortifications and how to lay siege to somebody else's forts. And so you can see in the upper right-hand corner here an example of one of the Vauban forts that are all over Europe that were near the French borders at the time. And this was really, I think, essential. You had the economies of scale of a larger nation state fostering this engineering enterprise, seeing the practical benefits of having more of a rational, scientific, mathematically based approach to engineering and decision making and organizing enterprises. And mixing that with the state. So you had really a state-sponsored profession and the rise of engineering schools sponsored by the state. And so you have the, in engineering, in civil engineering, it's the École Nationale des Ponts et Chaussées, the School of Bridges and Roads, okay? And the graduates of the School of Bridges and Roads go work for the civil service of the state in this problem area. And many of the equations that we are forced to learn and use as students came out of this. Navier, Dupuit, I'll talk about them a little bit later. The success of this was tremendous. Certainly this engineering approach made the French military much more successful. Other people took note. In the American Revolution, we were very quick to import French engineers, French military leaders to teach the American engineering corps during the Revolution and after. And the British picked this up in 1812. They formed their first engineering school. And of course, as Napoleon conquered much of Europe, he exported this way of thinking to the Dutch and to the Swedes and Spanish as well. So. I want to also point out this aqueduct, which is also in my background, was designed in 1766 by Henri Pitot. It's the same Pitot as the Pitot tube. So again, here's this tremendous consolidation and integration of the practical and the theoretical, the mathematics, the research, and by people who are actually going to go out and build stuff and do all the things you need to be a construction engineer as well. So really a great foundation for the engineering discipline in many ways. I want to focus a little bit on Claude-Louis Navier, who's one of the Navier-Stokes people, early 1800s French engineer with the École Nationale des Ponts et Chaussées and the École Polytechnique. Of course, he founded many of the fluid mechanics equations that we know and love. But I also want to point out that he was a failed bridge engineer. And here's a picture of the bridge across the Seine that he built in 1824. The articles that I've seen on this basically said he didn't include a big enough safety factor in the calculations. He had too much faith in the calculations and didn't have a big enough safety factor. So they ended up having to disassemble the bridge. And I think he wasn't allowed to build bridges anymore. I also want to point out that here's someone who's building bridges, deriving the fundamental equations of fluid mechanics, and also he had a very wonderful work in 1832 on how should you organize public works? How should the state of France organize public works? Should they have toll roads? Should they outsource it to the private sector? Should the state finance everything off the tax base? It should be by tolls. A really very thoughtful essay on the subject for about 15 pages. And then tragically, of course, he died at the age of 51. So you have to understand that these people, when they did this work, in all of these different fundamentals of the finance of these systems, of the mechanics of these systems, they were all just young, enthusiastic people. Kind of like graduate students, let loose in a sense, with some really important problems. Jules Dupuit, another famous engineer who many of you will have studied his equations and his assumptions in groundwater flow. He wrote in transportation. He's famous for the early theory of toll roads and tolls on canals, tolls on bridges, tolls on roads. He essentially wrote the founding work of microeconomics on consumer surplus in 1844. And so I love to tell my economist colleagues that my field founded yours. Really, engineers can say that because that's really true. He went on to become the chief engineer of Paris in 1850s and was responsible for many of the sewers there. If you ever go to Paris, I highly recommend a trip to the Musée des Gouttes, the Museum of Sewers. You'll see his name on one of the sewers. He did some really fundamental and great thinking on flood engineering in 1857, 1858. Really fundamental kind of systems engineering, systems thinking about flood management. Many, many years ahead of his time in quite a few ways, although there's actually some American examples of struggling with the same problem. And of course, the Dupuit assumption in groundwater, which he did about the age 65, actually. So maybe there's hope for me in deriving equations for mechanics. He has this great quote here that there is only utility when someone should consent to pay. He was trying to figure out this, the French state was building all of these canals, and he was trying to decide, well, when should we stop building canals? And you know, how much is it worth to build a canal compared to the cost? So both he and Navier actually were very fundamental in early conceptualization of benefit cost analysis, which is something we use all the time today in public policy. So all good things eventually came from some engineer at some time, I think. Modern engineering in the United States, I think, started with the United States Army during the Revolution, when they brought French engineers over to help the American Revolution build fortifications and actually lay siege to fortifications in the case of Yorktown. The first engineering schools were the West Point Military Academy, you know, because they had to have engineers for the military, and the first university kind of education in engineering was Rensselaer Institute in New York in 1850, and this again was imported from Europe, largely from France. In 1862, the Morrill Act that founded the land grant system of universities across the United States. University of Washington has a small amount of money they get from the land grant endowments from that time, I think, still as well. They, as part of that Morrill Act, it established the idea of the public universities in the United States having an applied engineering curriculum as part of it, you know, to go along with agriculture. You know, it's more famous, you see it more in agriculture and in Washington State forestry, but engineering is part of that. And so basically, since the Morrill Act, the American public universities have all had colleges of engineering, and that has been really responsible in the United States for mainstreaming engineering into what had been formerly just liberal arts colleges across the United States. And so I think engineering has always benefited from being in universities that aren't just polytechnic universities in the old French model, but are part of broader intellectual enterprises. We slowly started to adopt, I think, the mathematics of the French approach, French tradition, in the 1900s. It took us a little while to get as mathematically sophisticated as the École Nationale de Pont-à-Chaussée was in the 1850s, but I think we're sort of in that realm now. When I came to the Davis campus, we had some professors who would refer to engineering as the liberal science as opposed to the liberal arts, because we brought so many different sciences together in a fairly broad education, a broad science education as opposed to a broad arts education, humanities education. In modern engineering, we certainly rely a lot on universities as a source for new ideas and expertise. We're always in engineering, borrowing ideas from the science community, from the social sciences as well, sometimes political science for lawyers even sometimes. And we benefit from that kind of cross-training, cross-thinking. Engineering colleges are now the main way that we train engineers. Up until really only a century ago, even a century ago, I think an awful lot of engineers were trained by in an apprenticeship system, and they had very little formal education. And we have a little bit of exposure to organized problem solving. So I want to go through quickly some modern examples. First, urban drinking water. If you were to go back about a century and a half, we had a lot of death from drinking water. A lot of people died from drinking poor quality water. A lot of typhoid, cholera, dysentery. Basically, every summer, tens of thousands of people in the United States would die from unsafe drinking water. And the technology was developing, the germ theories were starting in the microbiology were starting to emerge. And the profession developed basically this thought about maybe we can learn from failures and we can bring some science and analysis and have some organized sets of improvement. There was essentially thinking along what we call today the multiple barriers approach, where certainly early in Seattle, before you added filtration and disinfection, there was, well, we'll just go out and get a really good water source. And then, okay, then we're going to add treatment and we're going to have a pipe supply so contaminants don't enter in the delivery system, chlorination, things like this. And how do those things go together? But there were a lot of consultants and state labs actually that were organized around this problem of how do we regulate municipal water systems and how do we sort of debug all of these different multiple barriers and make it so that they go well together in an economical way that provides a lot of reliability and quality and quantity of water at an affordable price. And by the way, also provide enough water supply that we can do firefighting in cities. There's a wonderful story about the city of Seattle's water system. It was originally a private system. And 2 weeks before there was going to be a referendum on should the city buy the private water system, there was a fire when the water system was not sufficient to put out the fire. And so the referendum passed resoundingly that the city should acquire the private water system, which originally took its water from Lake Washington. And then the Cedar River system was built off of that. In really central to this success in urban drinking water, again, coming back to people, is the pairing of these institutions, the local water utilities, with their direct accountability to the people. If we don't like it, we're going to vote to buy the water system and run it ourselves or privatize it if we like. But that local utility also could provide the funding, the wherewithal, motivated customers to provide the money in an organized and cost-effective way to provide the resources to run the system. But for the healthiness and the safety of the water system, often we found it to be much better to have some outsider comes in and does the inspections on the water quality and the environmental impact. And so we have a system where we have state and federal regulators coming in and to provide assurances that the water is safe and healthy. But for the financial stability and most of the engineering, we rely on local experts with local accountability to keep that working. So there's sort of an ecosystem of institutions that is behind making the engineering work, all of which have to have the right kinds of inspections and accountability and finance in the end. In all of this, there was a wonderful work of Hazen, which I'll highlight next. And he has this wonderful book that sort of assembled back in 1914 all of these different aspects of water provision. And he wrote this book for all of these cities and towns that were trying to develop safe water systems. And he very concisely labeled that book Clean Water and How to Get It. And if you look at that book, it has all these details. And so here's Alan Hazen, just an incredible person, and one of many, many people who were of that era, who were really trying to solve this problem. And they would go out and learn chemistry and physics and math and finance and law and probability, and they'd have to invent. The probability paper came out of Alan Hazen's work, trying to understand reliability of reservoirs. And you can see from this list that he basically has fundamental contributions in almost every aspect of urban water supply and indeed flood frequency. And then trying to put it all together in a package. So again, engineers as sort of the liberal scientists, in a sense, that is integrating all these other disciplines. We're kind of a discipline that integrates disciplines to solve problems in many ways, often with a quantitative and rational basis. Here's Seattle's water system, just to show an example of it. And I'll take this from a paper that I actually started when I was a graduate student and published when I was a professor, just to encourage all of you graduate students with your term papers, that many of them actually are quite good and can eventually become published. How we went from a private system to a public system in Washington, in Seattle, in the metropolitan area. Once the city of Seattle got a really good water system, it became very popular in the metropolitan area. And so you can see from this map that it sells water to 2 or 3 times the number of people outside of the city as in the city. This is true for Chicago. This is true for San Francisco. It's true for New York. These systems, with their economies of scale, became magnets for the city as well, selling water to the suburbs and making it cheaper and better for everybody, really. And really, we kind of have a mirror of this also on the wastewater side. One of the things you see with urban water problems is once you have water supply, then you have wastewater problems. And so sewers went through a similar process, which I'll skip through because I'm going too slowly here. And regional water management, we have a lot of examples of that. And I want to, of course, mention some of the work by Richard Palmer from his dissertation as well. So in regional water management, we've had a lot of success of engineering and reducing a lot of those death rates that we saw early. And I mentioned this, Steve Burgess. I could not give a presentation in front of Steve Burgess without mentioning Arthur E. Morgan, who was the consulting engineer that developed the Miami Conservancy District in the early 1900s and was the founding engineer for the Tennessee Valley Authority with the system engineering approach. I highly recommend his book in 1950 on the subjects. He really combined engineering, government, finance with a very systematic way of moving through the problem, in a very quantitative, thoughtful way to integrate the people, the finance, the physics, the land use, all aspects of it. He was a tremendous, outstanding career. And Steve Burgess has a wonderful paper in 1979 that treats him a little bit greater length. I want to mention structural engineering here. One of my former mentors, also Colin Brown, did some wonderful work on adaptive responses to failures. Again, one of the great things about engineering is we respond to failures. We make mistakes. We try to figure out why they failed. We try to integrate them back into the theory of how we understand the problem and the solution, and hopefully, and usually, come up with a better solution. So this is an example of the history of suspension bridges. Colin had a wonderful paper in '86 on this. So you can see the length to depth ratio of suspension bridges over time, getting bigger and bigger, and then they had to be stiffened, and then eventually this one failed. This was the Tacoma Narrows Bridge. And then after that, people were much less ambitious in their suspension bridges, but then as they figured out new theories of dynamics, they were able to be more ambitious again. So the structuring, sort of the social structure of the profession in terms of being able to learn from mistakes and then recodify these advances and get them distributed with universities and professional organizations alike is really important for us, as we kind of all know already. We have quite a few future challenges. Some of these are eternal. Okay, we have eternal problems of public health, economic prosperity, the environment for humans and ecosystems, and social political objectives of all the structures, be they the political power lust of Louis XIV or the populism that led to the acquisition of water supply systems across the United States during the progressive eras in the 1930s. We've always used engineering for social and political purposes, as well as these other sort of very fundamental purposes, which are in many ways eternal. Engineering is really part of the society, and engineering is successful or unsuccessful within a changing context. Projects that we think are successful when we first build them, we find out are unsuccessful as a society might have changed in the future as the objectives change. One of our problems, one of our challenges, we build stuff that lasts a long time, often lasts a really long time. They will last longer than the society in many cases that built them. The objectives of society, the economic structure of the society will have changed over the lifetime of many of our structures. And so our infrastructure, I think you have to see it as both giving stability to a society and building a foundation that it can add additional prosperity and health activities onto, social justice activities in our case. And it can provide this sort of stability that can both resist change that might be desirable and enable change. And part of our challenge as a profession is how to get the good out of that stability and the good out of that change without the bad out of overstability and the bad out of bad changes. Although, I think it's almost universal that any change has some good and some bad, but we want to have it on balance be good. And that's certainly a socially perceived kind of activity. So I'll come back to our challenges: public health, prosperity, the environment, and social objectives, social justice, economic opportunities. Engineering is really a wonderful profession. It always has been a way for people to come into the society and into the mainstream, contribute and change the society in better ways, improve it in many ways, even though sometimes we have deleterious effects as well. A few thoughts on being successful that I observe across all of these people is understanding the problem, the effort, dedication to understanding the problem you're trying to solve, the bigger problem you're trying to solve. Systems engineering of assembling all the pieces and trying to really work to find the most successful way of putting all of the technological and human pieces together, bringing in all kinds of new ideas in many cases, and not being afraid to bring in ideas from other disciplines. Again, engineering is most successful when we are a discipline that assembles other disciplines. And that, of course, requires that we talk to a lot of people and understand the kind of opportunities, limitations of all of these things. And I think communication is really important in all of this. When you're working with lots of different people, lots of diverse kinds of people and diverse kinds of disciplines, our ability to communicate, and this is where math has been really, really helpful for us in many ways to provide some quantitative understanding of things that people can really grasp onto that have some precision. And then I think because the kind of problems we deal with are eternal, we often have to be satisfied with partial solutions. Another great definition, I think, of engineering is doing better than we would have done otherwise. There are very few perfect solutions in this world, but we've done really well over the last few thousand years doing better than our predecessors in many ways. So partial solutions are still good solutions. Sometimes they're the best available solutions. Again, coming back to our question, I think, why are there so many fewer deaths in drought and floods? A lot of this is because of engineering, because the organization of society that the engineering profession has allowed, because of the transportation networks, the trade networks that have really founded on, the business networks that are also founded on engineering ways of thinking that have allowed many of these things, many improvements in much of life. We're seeing, I think, as an example of pandemics, old challenges always come back to us. So again, we've never solved these problems completely. This is a wonderful plot that I saw recently of what happened with the population of England and its per capita gross domestic product from the 1200s to the 1700s, and how series of plagues would just really set back the populations and quite often the gross domestic product per capita. We've sort of escaped a lot of that, I think, with trade and modern medicine, but we still have challenges with it, as we're seeing during this pandemic. I think many of us were surprised, and we're going to have future surprises as well. We're going to have old problems come back to us. We're going to have some old lessons that are eternal and other old lessons that mislead us. We certainly were going to have challenges of climate change, social justice, and new surprises to us in many ways. Hopefully not war, but we probably will have some. The conclusions you've already seen, so I can just take this as read and then leave you with some further readings. And hopefully this leaves a few moments for some questions.